assignments you have seen, maybe, maybe not. Assignment number 4 is up. You have 2 weeks to complete it. And it's due as usual, Monday in 2 weeks. Please note that I'll get to your question, Nehan. Please note that that is Monday after the reading week. And on Sunday of the reading week, we have a test. So test 2. So Sunday, November 1st, you have a test 2. And assignment number 4 is due less than 24 hours later. So I strongly suggest you start the assignment 4 now. In particular, because actually you're going to need to have this knowledge that you're going to acquire by doing assignment number 4 for test 2. Because in test 2, you're going to have lists and you're going to have strings, and lists are in assignment 4. So I strongly suggest you get it. And as usual, another reason to start early is that then you actually have help available through the office hours. Let me remind you that you just show up for the office hours. So if you go in Brightspace to office hours links, you're going to see office hours of everybody. You just click on the link and join the office hours. I hope you are taking advantage of help that is available for this, including the Mentoring Center study groups that they organize every week. I hope you do, because for example, for my own office hours today, I had only 2 people and one was a mistake. So I hope that I hope the reason is that you're more comfortable asking help from TAs and that you do actually go to these office hours to get help. Okay, and again, during the reading week, we will be running all the office hours as normal. So it's going to be, in terms of academics, you will be able to get office hours you will be able to attend office hours during the reading week. There won't be classes, but you will have office hours and no labs. Okay, so that's what I wanted to say about assignment 4. Another thing I wanted to draw your attention to is that I added a copyright information. As you've seen from my email that I sent you, some students post my assignments and tests on the web pages. You should know that all of this material is created by me. Every single one of these questions I created. And to post somebody else's material online, you need to have a permission, okay? And so starting with this assignment and all the remaining tests, you specifically do not have a permission to post anything from this class on internet. And this is typically the case. Something that doesn't belong to you, you should ask yourself, do I have a right to post this somewhere else? Okay. So do read these things. This reminded me of the violations that we have seen with Chegg in the letter that I sent you. I did get many confessions, and I'm happy the students confess. This is actually a learning moment. But now we are at a stage, let's call it stage 2, where I'm actually asking Chegg for the disclosure of information of those who posted the questions, to make sure that indeed, basically following up on that letter. So let me show you where that is at. Of course, I can't give you any private information. You'll never get any private information, but I'm assuming that you would know what's going on. So I submitted the owner code request to Chegg. I got information from them that they will disclose information once they get a letter from the dean. And the dean is confirmed that he will send a letter. So this is what stage we are at. To get information about every single question that was used for evaluation of assignment number 1, 2, 3, and test 1 that is posted on these web pages. Okay, so I hope we don't resort to this, and I'm guessing that people who actually attend the lectures, you guys actually don't resort to these tactics. Okay, so much about that. Today we're going to do while loops and solve problems with while loops, but before we do, let me see if you have questions. And it seems I already have a question by Nathan. Nathan, I'm going to let you unmute yourself. Go ahead.
Oh, hi, miss. I just noticed that on my exam schedule, I didn't have this class. So does that mean we don't have an exam for this class?
There is no exams. If you watched in lecture, we spent the whole first lecture talking about how the class is evaluated. And the
Okay.
class has 6 assignments and 4 tests. So you should
Okay.
review the lecture 1 slides that are posted on Brightspace, and the dates of the tests and the assignments and the grading scheme, everything is there.
Okay. All right. Thank you.
No problem. Next one, Juan.
Hi, can you hear me?
Yes, I can hear you.
Okay, so talking about the copyright information warning, what about the lecture videos that are posted publicly on YouTube? Is it okay if we share that to peers that may
Yeah,
have
you can
missed it,
share there is the reason I made them, otherwise I wouldn't make them public. I'm happy that people, if somebody want to watch the lectures, I'm really happy sharing. I'm not for copywriting. You can, in principle, I give rights for students to share anything if they're willing. If somebody wants to learn, it actually makes me happy, and I put it as public on YouTube exactly for that reason. If somebody either in other sections or anywhere else wants to learn, is interesting, this is a plus. I'm happy that you share it. So this is completely fine. This is only the things that I use for evaluations, that I don't want on internet, because then the main reason for that is to get it solved, right? So tests and assignments, you cannot share. Everything else is a fair game. I'm happy if people are using it to learn. I'm pleased with that rather than forbid it. So that's okay. Any other questions? Nehan, your hand is still up. Do you have a question? Another question?
Oh, sorry. I didn't put it down. My bad.
Okay. All right. If there are no other questions, let's start with the lecture. As usual, I'm going to block you from unmuting yourself to stop, just to avoid the noise. But towards the end of the lecture, I will unmute you so you can ask questions. So what we're going to do today is we're going to oh, I should block my chats. All right, so that's gone. Distractions are gone. Let's focus on the lecture. So what we're going to do today, we're going to learn how to use while statements, while loop, not while statement, while loops. And once you see while loops, basically that everything that you've seen so far in Python plus the while loop, with what you have seen, you can solve every problem ever solved. So every program ever written can be solved with what you have seen plus the while loops. The formal way to see this is that what you have seen plus the while loop is so-called Turing complete. All these programming languages that you use are equivalent under this. So what you can solve with one, you can solve with another. So for this, we need the while loop. You don't need fancy things like objects and stuff. In fact, you can code them yourself. Okay, so let's look at the syntax of the while loop. It's actually very simple. It's the same as one-way if statement, basically. So let's recall what was let's recall what, let's see, just a moment. I hear you, so I'm assuming something's wrong with me because many of you raised a hand. All right, so can somebody tell me what's wrong?
Yeah, the
your screen's frozen.
Professor.
Yeah.
My screen is frozen.
Yep.
If you could stop sharing and reshare again, that might.
Okay, let's try that. My screen is frozen. All right, let me. So if something goes wrong, I hope nothing goes wrong. Of course, I will post this as usual on YouTube, but let's hopefully we can fix this. And whoever is writing on the screen, please don't do that. So let me go to Zoom. Stop sharing. Let's try again. Share screen, desktop, share. Okay, how is this?
We can see
Much
you now.
better.
Okay, let's try. Okay, guys, if you're having problems, why don't you unmask? I'm going to still unmute you just because I'm with 130 people. We have somebody answering the phone, as you have seen in the past. It's understandable completely. But if you do see the problems, please raise the hand, unmask, just like you did right now, and I will know something is wrong. Thank you. Okay, so let's look at the syntax of if statement. Ignore what I have on the bottom. It's something that I'm gonna revisit. So syntax of a one-way if statement is if, and then you have some condition, and then you have some statements. One or more statements. So you have a block of code that is going to be executed if the condition is true. Okay, so the while statement is basically identical. While, and then you have some condition. It's basically a Boolean expression, something that gives true or false. If you get true, then you execute a block of statements. Okay, so the syntax is identical. The only difference is that in an if statement, when you have a condition that is true, you're going to execute this block of statements once. In a while statement, you're going to execute it as long as the condition is true. So while the condition is true, so if you say it in English, it tells you what it does. While the condition is true, you're going to execute this block of statements. When you come to the end of the statements, you always go back to the beginning of the while loop. You check again, is the condition true? If it is, you go in. So as long as you get a true condition, you execute a block. At the end of the block, you go back to the beginning of the while loop, check the condition, and so on. So the only time you're going to leave the loop is going to be when this condition is false, and then you leave the loop and you continue somewhere here. Okay, so that is the syntax of the while statement. So let's redo something, one of the early things we did with the for loop. Everything you can do with the for loop, you can do with the while loop. So one of the early things we did, that's what I was hiding here, if you can call it hiding. We had this, let me leave the syntax here just briefly. So it's like syntax is really like a one-way statement. So let's redo this code using the while loop. Okay. So what did this do? Recall that we had this countdown that goes from 10 to 1 and then blast off. So let's do the same thing with the while loop. So we are starting with number 10. You will see that the while loops are a little bit more, what is the word I should use? Pedestrian. You have to do things yourself rather than using some fancy function that is producing a sequence of numbers for you, like in a for loop. So you're going to set the variables yourself. I'm starting with the number 10. I want to then enter the loop. We're going to figure out what the condition is. And inside of the loop, I want to print. So first time I enter the loop, I want to print 10. So I put I there. So, and first time, if I enter it, we have to check the condition. If the condition is true, you enter and you print I. Okay. So what do you want to have here for conditions? So in the live class, normally I would ask the students, and most would guess. So when do you ask yourself, when do I want to enter the loop? When do I want to print this value I? Okay, so you want to do that because we are printing numbers 10 to 1. You want to do it as long as I is strictly greater than 0. You want to enter the loop. As you're outside of the loop, like over here, you want to print blast off. Okay. So let's run this. I'm going to remove the for loop and let's see what we get. Okay. So we created our first, normally, again in the class, even while I'm typing, there will be hands up, people realizing something's wrong with this. So what we did this here is we created our first infinite loop, okay? What it means is that every time we come back to the beginning of this loop, I didn't change. So all the time I'm testing is 10 greater than 1. That is always true and forever true. So this print 10 is going to run forever. And basically, as long as either your computer crashes or you run out of electricity, and if none of this happens until the end of the world, okay? So this is really infinite loop. So what happens here every time, nothing changed. So we have every time you come back here, we have 10, is 10 greater than 0, that's true. So it's identical to having this, right? While true means you have an infinite loop. It's always going to repeat what's inside of the loop. Okay, so as I said, with while loops, you have to think of yourself what you want to do inside of the loop and update the variables a little bit more pedestrian way. So what do I want? After I printed I and the beginning I is 10, the next number I want to print is 9. Then the next number is 10. So I better update I to I minus 1. Okay, this is still printing, so I'm going to stop it now. So let's see what happens now. So now we actually managed to solve this problem. Every time we enter the loop, I is 1 less than in the previous round. So indeed, when we get the case that I is 1, we're going to enter the loop, print 1, and I becomes 0. And as always, at the end of the block of a loop, you always go back to the beginning of the loop. But this time is 0 greater than 0 gets tested, that that's false. And we get out of the loop. Okay, so that's the first example that I wanted to show you with a loop, but let me now show you more realistic things, something that happens all the time, where while loops are really a way to go, so much so that in the assignment number 2 and 3, I coded that part for you. It's the part when you're communicating with the user and you don't know if they're going to follow your instructions. So you want to keep on repeating the question as long as they're not giving you the answer that you want, right? A typical example is tell me yes or no, and they're distracted and they're giving you something that is not helpful for you. So you repeat a question, okay? So let's see how to code this. So imagine, for example, that you just displayed the airplane tickets and you want to say, oh, what do I have here? Yes or no, do you want to buy this ticket? Okay. So, and we capture this in the answer, variable answer. So what we want, if what is stored in answer is yes or no, we are good to go, right? The issue is that if the user is distracted, it doesn't give us yes or no, that we should be repeating this question, possibly infinitely, if they for infinitely long time refuse to give us yes or no. So let's do that. We have while, so I want to be repeating something. So while, and then we have some condition. We're going to determine what this condition is. So when do I want to repeat the question? When do I want to enter the loop? So I want to enter this loop if what is stored in answer is neither yes nor no. It's only then that I want to repeat the question, right? So first of all, inside of the loop, as I said, we want to enter the loop. To determine what condition you should have here, you first want to ask yourself, what am I doing in this loop? In this case, I want to give an error message. Only yes or no is accepted, and then ask the question again. So we can print something like, what do I have here? Incorrect input. Please answer yes or no. Okay. And then you repeat the question. So we put this one again. Okay. So this block of code, we want to execute it if the answer, as long as, so while this answer here is neither yes nor no, I want to be repeating this. So that's what the condition should test. If yes is neither no nor yes, then you enter the, that's the only condition under which you should enter the loop, because if the answer, what's stored the answer, if what's stored the answer is yes, you shouldn't enter the loop. If what's stored the answer is no, you shouldn't enter the loop. You know, you got the answer that you wanted. In that case, actually, you should be out of the loop and I don't know, print, I don't know, next step is, and so on. Okay. So what is this condition here? We want to enter the loop if something, in this case, if something that we don't want happens. One of the things that we don't want in the answer is not equal to yes. Okay, so here we ask them in capital. I'm going to repeat this. Another thing that we don't want is that answer is not equal to no. Okay. So now we have to determine here, what do I put here? Okay, so these are two events. If neither of them, if answer is neither yes nor no, I want to enter the loop. Okay, so it's neither yes nor no. Okay, so what do I put here? Is it and or an or? I have to glue, I have two conditions. How do I put them together such that when I enter the loop only if answer is neither yes or no? Okay, so when I ask this is class, very often, almost always I get an or. So let's check that. Okay, so let's test the program. Let's see when it works and when it doesn't work, if it doesn't work. If I enter some nonsense, we repeat the question. I answer more nonsense, we repeat the question. Okay, I answer yes, we still repeat the question. That's not what we wanted. Okay, so let's see why that happened. We have here yes not equal yes. That's false. But yes not equal no is true. And if you use or, false and true will give you true, and you're going to enter the loop. That's not what you want. What you want is to enter the loop when both of these things are true, when you not yes and you not no. Because if one of them is true, so if one of them is true, that means that you are yes or no. So you should use and here. It's demonstrate how important it is to understand these Boolean expressions. Okay, so let's try this. Nonsense, it doesn't accept it. Nonsense, it doesn't accept it. But now if I do no, for example, it does accept it. Okay, by the way, at this point, let me mention that something that you are expected to do, you were already expected to do previously and show you how to do it, is that we would like normally to process any kind of yes. And in this case, because I'm really only comparing it with the capital yes, it didn't accept it. And easiest way to deal with this, just to turn everything into lowercase. I turn whatever answer the user gave me to lowercase and I compare it to lowercase. Lowercase no. Okay, so now it's going to accept any strange thing like this because it first connected it to yes. Okay, so this is the solution for that problem. By the way, there's a different type of, you can write equivalent Boolean expression. Really, you design it in the way that is more natural for you. So here's another way to design a Boolean expression for this. And this is your ask yourself, actually, why am I, when am I happy? I'm happy when I get yes or no. That's what I want. So I don't want to enter a loop then. So I test when am I happy? I'm happy if I get yes or if I get no. So if one of them happen, remember, I now want if one of them happen, I'm happy. Then you use or. If one of them is happening, if I get yes or no, if one of them happen, I'm happy. So I'm testing that. So if one of these things happen, yes or no, I'm happy and I don't want to enter the loop. So in other words, when do you want to enter the loop? When this does not happen. So you negate that Boolean expression. So these two are identical, right? The one that I had before and this one. This one is saying, I don't want to enter the loop when I get yes or no. I don't want to enter the loop now, so I do not of if I get yes or no, I don't enter the loop. Okay, so when do I enter the loop? When I don't get that, when I have a not of that expression. So these two Boolean expressions are equivalent. Let's see, let's try something else, and we get that it's working. Okay. One last thing I want to say about this example and actually about your assignment number 4, you will notice that it says that you cannot use break and continue. Break in particular, well, it says both, but really the one that I would like you to not use is break. There's nothing terribly much wrong with break statement. Break statements just jump out of a loop. But if somebody knows what they're doing, there is some legitimate and justifiable uses for break. However, most of the time when students use it is because, in my experience, not everybody, of course, is because they're trying to avoid designing a Boolean expression, to write a proper Boolean expression to test when you should be in the loop or not. Let me demonstrate how you can solve this in this way. You can say, oh, while true. So I'm going to always be entering this loop. Then I'm going to see if I should be there. Okay. I'm solving the same problem. So we are here. You just ask the question and you're going to say, let me repeat this loop. I'm just going to enter the loop and see how it goes. Okay. Then you go inside and say, but actually, if the answer is yes, I shouldn't be here, right? I shouldn't be asking the question again. So you do break. Break means jump out of the loop. Okay. Okay, let me continue. Oh yeah, but actually I'm also happy with the no. I shouldn't be here if I get a no. And you do, oh, if answer equal to no, let me jump out of here. I shouldn't be actually inside of this. So if neither of these things happens, okay, then you say, oh, actually, yeah, now I should be in a while loop and should be asking the question again. So this is the reason I said not to use a break loop, because this is part of your learning, that you should learn how to write proper Boolean expression and figure out when you should enter the loop and when you should not enter the loop, for example. Okay, and by the way, there's also scientific papers in computer science community which prove that if you're using break statement, once it's compiled, the code, it increases the complexity of the compiled code, but this is a bit beyond, it goes to the architecture of the computer, it's a bit beyond what we're covering in this class, okay? So there is actually a reason other than learning not to use break, okay? In some ways, it behaves like a go-to, for those of you who know this ancient command that is removed from every programming language because it's so expensive once you to execute. Okay, it has a negative impact on executions of the program and their speed and efficiency. Okay, so that's that example. So let me move to the next example I wanted to show you. So one of the things that we did when we were doing strings was to, okay, let's write a function that prints all the vowels. Let's write a function that counts the vowels and so on. So, oh, by the way, before I go there, it reminded me. So now that you saw at least two examples when you use a while loop, you may ask yourself, so when should I use a while loop and when should I use a for loop? In particular, you just told us that everything that you write with a for loop, you can write with a while loop. The answer really is that, one answer is that you should use whatever you feel most comfortable for, whatever is going to make you correct code and efficient code. Correct first and then efficient. So whatever works for the type of problem that you're solving, and how you're going to solve the problem again is based on individuals. So that's one answer. Another answer, if you're unsure, is that a good rule of thumb is that if you don't want to know how many times you want something repeated, that you should use a while loop. So this is actually a perfect example. When you're asking for a user for input and they give you incorrect answer. So you have no idea how many times they're going to give you incorrect answer. Maybe they're trolling you and they're going to do it a million times, and you still, your specifications say that you should be repeating your question. So you, in this one, you really do not know a priori how many times your loop is going to be executed. So that's a good rule of thumb. Jason, you should keep your questions to the end. I'm going to take the questions at the end. So just remember your question. So you should keep, you don't know a priori how many times loop is executed. One example, when people often use for loops, is if they're looping over individual element of a string, if they're looping over individual element of the list. That's because if you really just want to visit every element of the list, you know that you're going to execute the loops. Basically, the number of times you're going to execute the loop is the number of elements in the loop. So number of elements in a list. So if your list is L, you're going to execute it len of L time. If you have a string S, you're going to execute it len of S time. So these are some rules over the time of when you should use one or the other. But in general, for yourself, just use whatever is going to make you write correct code, whatever is natural for the type of solution you're building. And later on, once we learn about efficacy, think of that too. But that really has nothing to do with the type of loops you're using. That has to do with number of time loops are executed. Okay. All right. So let's move to the next example that I wanted to show you, which is let's say we want to write a function that I call a print until vowel. So what does this function do? Is I have a string S. I want to, just like we did when we first learned about for loops and over strings, I want to print the elements of a string, but and I want to print them one by one, but the first moment I encounter a vowel, so the first vowel encounter, I want to stop. I'm not going to print anything after that. I'm not going to print that vowel nor anything that comes after. Okay. Which one to use, which loop to use, for loop, while loop. You certainly can solve this with a for loop. You still can go through all the elements of a string. Inside, you test, are you a vowel? No, you print it, no. But in first time you encounter a vowel, you set some flag to false that you know that, or true, however you're testing, such that you put a mark for yourself that you encounter the vowel, and next time you enter the loop, if that flag is set that you already encountered the vowel, you just don't print anything anymore. Okay, that's one way to do it, but you still, for example, would be visiting all of those letters for no reason. Let's say if your first letter is a vowel, you're still going to visit everything else in that type of solution. Or you can say, oh, I can break out. Well, I guess that's a good reason to break out, because you are stopping your program from going through all the other elements of the string unnecessarily once you find a vowel. Or we can argue, okay, in this case in particular, I really don't know when I'm going to stop looping, because I want to stop reading the elements of the string when I encounter a vowel, and I don't know when that's going to happen. So let's use a while loop in this case. And after all, it's a lecture about the while loops. Okay, so I want to go through the elements of this string S. By the way, hopefully by now, you know what a type contract is. S is a string. And the description says you print letters of a string one by one until you encounter the vowel. It doesn't say to return anything. So what's going to be a return type is none. The function doesn't return anything. Okay, so how do we solve this problem? I look at the first element of the string, test if it's vowel. If it's not, I print it. Next, if it's vowel, I stop. If it's not, I print it, and so on. Okay. So let me say that that for this solution, I want to be generating indices such that let's say first thing I want to print is S of 0 in case it's not a vowel, right? So what I want is that again, with while loops, you have to keep track of your positions yourself. So for that, you use variables. So I want to start in position at index 0. I'm going to use I for an index. Then I want to enter the loop, and I'm going to print the characters of the string. So we're going to leave condition for up to later. So assuming that I entered this loop, I want to print this character in position I. So first time I enter the loop, I 0, if I enter it, this is going to print S of 0. So I want that, right? So every time I enter the loop, I'm going to print element in that position. Okay, so if I first printed S of 0, next time I enter the loop, I want to print S of 1. Next time I enter the loop, I want to print S of 2. So I better update myself I, right? So after I finish printing S of I want to update the I to the next I. So when I was 0, This is going to change I to 1. So next time you enter the loop is going to be 1. Okay. So the only thing that we're missing here is this condition. You ask yourself, when do you want to enter the loop? Because certainly if S of I, if I had a word such as, what word is a good one? Doesn't cross my mind. What word starts with a vowel? Okay. Aha. So if I had the word aha, S of 0 is already a vowel. So I don't want to enter here and print S of 0. So this condition is saying you should be entering the loop as long as the current letter we're looking at is a vowel, is a consonant, so not a vowel. As soon as we see a first vowel, we get out of the loop and print, I don't know, goodbye, just to indicate for ourselves that we are done with this. Okay, so let's see. So the condition should be, I want to enter the loop if I'm not a vowel. So as long as S of I, the current letter I'm looking at, is not in, so not one of the vowels, A, E, I, O, U, E, I, O, U. Okay, so as long as it's not a vowel, I enter, it means it's consonant. Well, I guess it means it's consonant if it's really a letter. Let's assume that these are really letters of English alphabet. What's in S? Okay. So let's see if our code is working. All right, so print vowels, print until vowel. If I have something like, all right, I have a couple of consonants, then I have a vowel, then I have something like this. So hopefully my program prints all of these, and then once it encounters A, it doesn't print anything. I don't know what I did this here. Okay, so right now, actually, our program is correct because the string that I just put there starts with A, so it doesn't print, starts with a vowel, so it prints nothing. So the case is when we start with the vowel work. Let's see if we have something else where I have a couple of vowels before that. Indeed, it prints these 4 vowels and then it stops. If you wanted these to be printed one after another, like kind of a word, hopefully by now you know that you can modify what Python does. If you want them to be next to each other, you can just say put an empty string, don't move the cursor. So if I run that, okay, you see that, and here you can say, but this goodbye message start with a new line. This is just on the side. All right, so it prints LJKS, it counters the first vowel and doesn't print anything anymore. So far, this seems to be working. Let's run it to another example. Okay. All right, indeed, it prints everything up to a vowel, but this string does not have a vowel. And in this case, it really is doing everything correctly, but then it crashes and you get that infamous index out of range error. Okay, so let's figure out what happened. This string has 3 characters. And so the positions that we want to access in the string is 0, 1, 2. These are only viable indices and positions to access. So let's see what happens here. S of 0, print S of 0. It's not a vowel. So every time you're going to get a true for this. Then I becomes 1. S of 1, it's not a vowel. You print it at I becomes 2. S of 2 is S. It prints S. Then I becomes 4. We come here and we try to read S of 4. Let's look at this string. S of 4 doesn't exist. Okay. In fact, sorry, it becomes 3. S of 3 doesn't exist. So this is 0, 1, 2. When I is 2, this S was printed, then I becomes 3. You come here, you try to read S of 3. That doesn't exist. So there are 2 conditions under which you want to enter the loop and try to print a character. One is that you didn't encounter a vowel. And then the other one is that you still have some characters to read. that you didn't run out of a character. So you have to, again, this really demonstrated you have to check everything by yourself when you're using while loop. Okay, so what we want to do, we want to enter the loop as long as we didn't run out of character and the current character is not a vowel. How do we know we didn't run out of character? Well, that's if I is strictly less than len of s. Okay, so I want to enter if this is a valid position and s of I is not a vowel. Okay, so let's check that. All right, print until vowel. Let's see if it works on this example now, and indeed it does. Now it simply doesn't enter the loop when we run out of character. By the way, hopefully some of you notice something interesting here happening. So when I is 2, that's when we're looking s of 2 is s. When I is 2, 2 is less than 3, so len of s is 3, so this is true. And s of 2 is not a vowel. S is not one of these. So you enter in a print s here, letter s, because s of 2 is s. Then I becomes 3. You come here, 3 less than 3, that's false. But we have one Boolean expression here. And we also have to evaluate this part s of 3. You may ask yourself, how come Python didn't crash? I mean, you're still trying to read this s of 3. That's because Python does so-called lazy evaluation. What that means is that if you have two Boolean expression glued with an and, it's going to check first. Remember, when you have an and, both have to be true in order to get true. Otherwise, you get a false. Okay. So if the first one is false, there's no point in looking at this one because you already know the answer. So that's what, like, why they call it lazy evaluation. If I get a false in the first condition, I'm not going to even check the next one because I already know the answer. So in our case, 3 is less than 3 is false. There is no point is evaluating this. So Python is going to not do it, and it's not going to crash in s of 3. So that actually tells you that although mathematically these expressions are the same, if you change the order and write it like this, now it would crash because it would test first, is s of 3, and boom, it crashes. You're trying to access s of 3, okay? There is a way to write this without relying on lazy evaluation. It's easy to avoid it. I will just put it as a second solution to this problem when I post this on Brightspace, so you can look at it. How, if for some reason you don't want to use this you don't want to rely on the concept of lazy evaluation. Okay, but right now I want to move on something else. I want to show you something called collatz conjecture. So first of all, what's a conjecture? What's the word conjecture? So often in class I ask this, and my impression is that most students don't know what it is, at least don't know formally what it means. So conjecture is a statement that most people, either, you can even say general public, but typically this relies to science and kind of academic disciplines. They believe it's true, but they cannot prove it's true. Okay, so conjecture is a statement that you believe it's true, or majority of people believe it's true, but cannot prove that it's true. If you manage to prove some statement, then it becomes a theorem, at least in mathematics, right? So if you have a conjecture, so something you believe is true, but don't know if it's true, if you cannot prove it's true, if eventually you manage to prove it, it becomes a theorem, okay? So this collatz conjecture, it was first asked and conjectured to be true in 1937. So more than 80 years ago, a mathematician, German mathematician, Lothar Collatz, asked this question. I'm going to explain it to you. And we still don't know the answer. It's still a conjecture. It's still not a theorem. We don't know whether this is true or false, even though there is lots of experimental results that point to true, but we have no idea if it's true. Okay, so let me explain you what it is. It's easiest on the example over here. You have a formula. Formula is simple enough. But it's, as always, things are easier to explain on an example. So let's see what we're looking at. Okay, so here's what a conjecture says. It says if you start, here's a process that you're going to do. Let's say I give you a number n, and this n is a positive integer. Okay, so number 1, 2, 3, one of these numbers. So any positive integer, arbitrarily big positive integer. And the procedure that you're going to do, if n is even, I want you to divide n by 2. If n is odd, I would like you to multiply n by 3. So do 3 times n plus 1. Okay? So if n is even, you do this operation. If n is odd, you do this operation. Okay, so these are the rules. And you want to know, the collatz conjecture says that no matter what number I start with, what positive integer I start with, and I apply this operation, I'm going to get a sequence of numbers, right? So if I start with, let's say n is 12. If I start with n is 12, so first number is 12, it's even, therefore I should divide it by 2. So I get a 6. 6 is even, so I should divide it by 2, the rule says. I get a 3. 3 is odd, so I should multiply it by 3 and add 1. That's a 10, okay? So the rule, the conjecture said that no matter what integer you start with, that you are going to eventually get down to 1, okay? So let's complete this for 12 and see if it's true for 12. So 10 is even, so we divide by 2, we get a 5. 5 is odd, we multiply by 3 and add 1, so we get 16. 15 plus 1 is 16. 16 divided by 2 is 8. 16 is even. 8 is even. We divide by 2, we get a 4. 4 is even. We divide by 2, we get a 2. 2 is even. We divide by 2, we get a 1. So collatz conjecture is true for 12. Okay. The conjecture says that this is true for any integer. If you pick a number like 0, these are not numbers. Let me pick some number. Any number you pick, the conjecture says that no matter what you start, if you apply this set of rules, you're going to get a sequence that eventually the sequence comes down to 1. Okay. It shouldn't be that obvious that this is true, right? Because when there's equal number of even numbers and odd numbers, and when the number is even, we're only going down by 2, but when it's odd, we're going up by 3 plus 1, okay? Anyway, so we still don't know the answer to this question, but what we can do is we can write a little Python function. Let me call it collatz. I'm not good with spelling, so I'm gonna always look at my notes. All right, so let's write a function that given a number n. So what I want to do is apply this operation. Okay, so I want to test if this number satisfies collatz conjecture. Does the sequence goes down to 1? Okay, so we have a number 1. So let me first do the operation, right? So if n is even, so how do I test if a number is even? If the remainder of division with 2 is 0. In that case, the new number in the sequence that I produce is n divided by 2. I might as well do integer division. I'm not losing anything, and I'm staying in a set of integers, because if n is even, the result is correct, right? So the new number is n over 2. New number in the sequence n is n over 2. Otherwise, we know that the number is odd. And in that case, the new number in the sequence is 3 times n plus 1. Okay, so we want to repeat this. What is the condition? Okay, so we want to be repeating this piece of code as long as what? When do we want to stop? Okay, we want to stop when we get down to 1, if we ever get down to 1. Because if we get down to 1, that means that collatz conjecture is true for that number n. For example, when n is 12, we have seen that eventually the number produced here is 1, and we should leave the loop. So We want to enter the loop as long as you're not equal to 1, because you want to then produce the next number. So if we ever get out of this loop, return true. If we get out of the loop, that means that n is 1, we reach 1, and this number, particular number n for which we are testing collatz conjecture is true. Okay, so let's at least try it for 12, for what we have seen already. 12 is true. We can even, just for our own record, print n to see what sequence we get. And also print, make sure here that really we get 1. So let's see what we get. That's the sequence that we computed by hand. 12, 6, 3, 10, 5, 16, 8, 4, 2, 1. That's the one that we did by hand. By the way, let's look at this loop here. So try to answer this for yourself. Is this an infinite loop? We have seen the beginning of class that infinite loop, the one that was printing 10, 10, 10, 10, 10, 10. Okay, so is this an infinite loop? You may say, well, we just saw it that it's not for 12. But something is an infinite loop. In this case, it depends on n. Something is an infinite loop if here, in this case, if for some value of n, this loop is infinite. It's going to never, this condition will never be false, will never leave the loop. So if for any value n, this loop will execute infinitely many times, or you can use times. If for any value of n, this is an infinite loop, then in general, your solution has an infinite loop. So is this an infinite loop? Try to answer that for yourself while I have a sip of water. All right. So I hope that some of you at least can see that that's an optimum, that's the open question. Nobody knows. That's exactly equivalent to collatz conjecture. If collatz conjecture is true, then this is not an infinite loop for any n, because for every n, we eventually going to go down to 1 and leave the loop. So it's not an infinite loop. If the collatz conjecture is false, that means that there exists a number n such that we will never go down to 1 here. Therefore, this means this infinite loop. So the question is, this loop here that we just wrote, is it an infinite loop? Is identical to the collatz conjecture? And nobody knows the answer to that. Okay, so we don't know if this is an infinite loop. Okay, let's test it on a few more numbers. It's not just 12. Let's pick some bigger number, 3,251. Okay, so it prints the sequence. Oh, we are getting to 10,000 even, but eventually it does get down to 1. Let's pick a bigger number, 100,003, and in printing the numbers, and it seems to be, oh, it goes up again. Okay, eventually goes down to 1. So you can even pick, I don't know, a couple of million. Here, this is much bigger than a couple of million. So let's see, this is 1 million. Let's do 10 million, 100 million. Okay, so it's printing these things. It's actually printing that is slow. So we don't have to print, but okay, for the thing of 100 million, we seem to get to 1. So let me at least put them in comment, this print, so that we can try some really huge numbers. Okay, so let's test if, let's add many digits here. This huge number, maybe I have a syntax error. Oh, because I'll put a letter O here. Okay, so it's true. It's actually very quick, right? You see, it's much quicker if we don't have to print. So this particular number, which I don't know, billions of billions of billions, it also turns out to be true. So what you can do, you can say, okay, let me test if collatz conjecture is true for first. Now that you have a function that tests one number, let me test first million numbers. Let me test if collatz conjecture is true for first million numbers. Okay, so let's do this. for I in range, I want to go from million, 1, 2, 3, 1, 2, 3. Because I want to go to million, I better put 1 there. So this is going to produce numbers from 1 to million. Each time we produce the next number, we enter and we test collatz number with that particular number. Okay, if we ever get out of that loop, okay, on this loop here, that means that each one of these numbers eventually returned. Okay, so we can safely write the conjecture is true for the first million numbers. Okay, so why are we safe to write this? Because if we ever come to print this, it means that for all these numbers, this loop, we exited this loop. It means this loop reached 1, all of them, for every single one of these numbers, we return true here. If for any one of these numbers, let's say 200,000, we made a call, every time we entered the loop, we made a call, let's say call us 200,000, and if the conjecture is not true for 200,000, the program would forever be stuck in this loop. We will never get to this line, print the conjecture is true for the first million numbers. So let's run this experiment. It's thinking. And while it's thinking, let me ask you one question. So I hopefully now made argument that you understand that if we ever print, so it looks like, so it did print. So if we, argument that if we ever print this, it means that collatz conjecture is true for the first million numbers. But let's say this didn't happen. And let's say we sit here for 10 years and nothing gets printed. Nothing is happening. The program is still doing something. Can we conclude that collatz conjecture is not true for some number between 1 and a million? The answer is no. It could be, maybe, let me again pick 200,000. It could be, except that we know it's not true for 200,000. But let's imagine, here's why it's not true. It could be that for 200,000, the sequence that gets created so long, it has 10 to the 1,000 elements. To test 10 to the 1,000 elements, we, in Python, to test all of those, to even produce 10 to the 1,000 numbers, Python is going to take 100 years. So maybe the sequence is 10 to the 1,000 integers long, but at the end of 10 to the 1,000 number, it does go down to 1. So if you do print this, we know that the conjecture is true for those first million number. But if you're sitting there and nothing's happening, that's not a proof that it's not true. Okay, so let's pick some bigger number. 5 million, let's pick first 5 million numbers. In fact, because we tested all of the first million numbers, we don't have to test them again. So we can start with a million, 1, 2, 3, 1, 2, 3. So let's test if the conjecture is true for the first 5 million numbers and so on. In fact, this conjecture has been verified for the first, I don't know, huge number, 10 to the 20 first integers, because they use lots of tricks to reduce the number of operations that you have to do to test this. But in general, we'll quote one of the most famous mathematicians of the 20th century. It was a Hungarian mathematician, Paul Erdős. He was really a superstar of mathematics, if you can say that, and was considered one of the best mathematicians ever. He said that this problem, that mathematics is not ready for this problem. We are nowhere close to understanding. So the problem that you can explain to a child, we are nowhere close to understanding and proving if this is true or not. Okay, so this is still working. It's still proving it for, it's still running for the first 5 million numbers. That's it, what I wanted to tell you about collatz conjecture. And last thing I wanted to code for this class, and I can let the program run while I'm explaining to you what I want to do next. Oh, okay, so it's proved. All right, so it proved. It printed, except that my code said first million, but I should have changed the printout. It says first 5 million. So with our own experiment, we tested the first 5 million numbers and showed that that the collatz conjecture is true for the first 5 million numbers. So for the end of the class, what I want to do is code a game Completely different problem, has nothing to do with collatz conjecture. I'm going to call it, we're going to call it a guessing game. And it's a simple one. You know, we're left with 20 minutes. It's a simple game. I want to write a function. And the game is like this. The computer picks a number from 1 to 1,000. Okay, it could be from 1 to 1,000,000, but the one that I'm going to code is from 1 to 1,000. So at the end of this, we're going to play a game. So computer is going to pick a number from 1 to 1,000, and our goal is to guess a number. And of course, guess it in as few guesses as possible. And of course, we want to win. And you win if you guess correctly. Okay. Typically, you have a certain number of tries, so you win if you win if you guess correctly in the given number of tries. Okay. So what did we say the first step is? Hopefully from your previous assignment, you learned that Python has a module to generate random numbers. So I'm going to import random module, and that you already used the function called rand_int. So we said the first step is Python should generate a random number. So we're not going to know what that number is. So random, it's in a random module. The function is rand_int. And if you give it two numbers like this, it's going to produce a random integer between 1 and 1,000 inclusively. So numbers in this range, including 1, 2, 3, up to and including 1,000. So any number of these is fair game. It's going to pick it at random. Okay, so you may even want to print a message to a player that says something like, what do I have here? It says, I'm thinking of a number in the set 1, 2, 3, I don't know, 1,000. Okay, all right. And we want, of course, because of what we want to be comparing, did my guess, is it equal to this random number? We want to store this random number in a variable. So X is a secret number, okay, that we don't know and we want to guess. So obviously the next thing in your game is you want to ask a user to give you a guess. We know how to ask a user for a number. You say, what do I have here? Try and guess. Let's just say try and guess. Okay. In this case, we are not going to be worrying that they're going to follow the instruction. We're really going to assume that they're going to give us a number between 1 and 1,000 inclusively. So I'm going to immediately just convert it to an int. And that's my guess. So whatever the number they give me, that's going to be stored in a guess. So what do we want to do with this? The game is that if you guess correctly within your number of tries, you win. If your guess is too high, higher than the random number picked, you put that message, it's too high. If it's too low, you put that message that it's too low. So what we want to do in this game is, if guess is too big, well, I have here first, let me stick to my code that I will post. If your guess is too small, then you just print the message wrong and too low. Okay, that's a message you're going to print. Else if your guess is too high, then you're going to print a similar message, but this time you're going to tell user that their guess is too high. Otherwise, fine. The only other opportunity or possibility, if the guess is not less than X and not bigger than X, well, the only possibility is actually that your guess is correct, that it's equal to X. In that case, you print, I don't know, what do I have here? You win. Great work. Okay, so we already coded a game. A boring one, it has only one round, right? You have, so, but still, we can already play it. By the way, looking at this, hopefully you know that this function doesn't have any parameter, doesn't expect the call, there are no parameters, so you don't expect any values when you make a function call. So this is what you write, and does it return anything? So it doesn't return anything. So here's a type contract. Okay, so rather than calling this in a shell, let's for a change actually put it in a main. Let's use it here. Okay, and we call the guessing game. Let's play one round of that game. Okay, try and guess. Oh, I don't like when these things, I don't put a space there, also rerun it. Okay, try and guess. At this point, we're going to try to play this game together. At this particular point is really boring one. At least then we're going to do the actual one with more tries. Okay, so I have 1,000 number and I have, this has only one round. I have one guess. So at this point, because I would like us to play this together, I'll allow you to unmute yourself. So give me a number between 1 and 1,000. Anybody? Just speak up. Just give me a number.
124.
505.
505. Okay, it's too high. Game over. We lost. Okay. By the way, what's the probability that we win in this game?
It's 1 in 1,000.
Exactly. Our chances to win this, it's 1 in 1,000. So not only is there is such a thing, hopefully you're aware, many of you are playing games, that it's called a winning strategy. So a game has a winning strategy if no matter what the game does, you have a strategy such that you will always win, no matter what. Okay, so clearly this game, there is no winning strategy. In fact, you cannot guarantee that you will always win. In fact, your chances to win are 1 in 1,000. Okay, all right, that's just on the side. We're going to come revisit this. All right, so this game is really bad, right? It has one round and your chances are terrible. By the way, this is studied in the game design. You want to design a game such that, first of all, it's not too easy, that you don't win too easily. Second of all, that it's not too difficult like this one, that you never win, right? So there is a perfect balance of this that you want to do. That person is making a progress, but it's not too easy. Okay, so typically in a game, the way to modify this game so this at least is a little bit reasonable is if you give a player a number of tries, not this. This is equivalent to giving a 1 try, okay? So you want to be repeating this. So what I want to do is I want to be repeating the code, the thing where I'm asking. So once, if they're wrong, over here, I want to ask them for a guess again and repeat this code. Okay, so let's write a while loop for that. I'm going to indent this code while, and then we're gonna figure out the condition. When do I want to enter this loop? Okay, so normally one of the things you can do to make the game like this is reasonable is that you give a number of tries to a person. The previous game was equivalent to having a 1 try. Okay, so we're having a game that with 1,000 numbers, and we're gonna give a person a certain number of tries, okay? And we don't want it to be 1. So how many tries do you want to give it to a person, to a player? Anybody?
7.
7 tries. Okay. Okay, so we give it 7 tries. Okay, so they already made a guess here, so I better reduce the number of tries by 1. Okay, so new number of tries is tries minus 1. Okay, so when do I want to enter the loop? Notice that in the loop, I'm asking them again to give me a guess. First of all, when do you want to ask them again to give you a guess? Well, if they already haven't guessed it correctly. So I want to enter the loop if their current guess is incorrect. That's one reason to enter the loop, because the current guess, if the guess is not equal to X, okay, so then you want to enter the loop, and as part of it, you're going to ask them to guess again. And another condition under which you're going to allow them to have another guess if they have more than 0 tries. So if the number of tries is more than 0, you get to guess again. Okay. So we coded that part. You're going to enter the loop. Your current guess is going to get tested. And you are going to, since you have more than one try, you're going to get asked again. Okay. So once we leave the loop, we should give a person a message, did they win or not? How do we know if they won or not? If we get to this part of the call, so outside of the loop, there are two reasons that both of these have to be true for me to enter the loop. I have enough tries and I was wrong. Then you get to try again and make another guess, right? So it could be that I left the loop because I ran out of tries. So in that case, I lost, okay? But it could be that I ran out of loop because this is false. If this is false, this means that I made a correct guess. So I'm not entering the loop again to ask the question. So the message is, once I'm outside the loop, if the last guess I made is equal to X, if that's the reason I've left the loop, then I should print a message, you won. What do I have here? You win. Lots of exclamation points for dramatic effect. Great work. Okay. Otherwise, all right, otherwise, it means that you left the loop. So if your guess was incorrect, but you left the loop, it means that the last thing you guessed was incorrect and you out of tries, it means you lost. You lost. You are not a very good guesser. Just for the purpose of, actually, let me ask you something. So I just explained what's a winning strategy. Winning strategy is something that you can say for a game. So here's a game, a fixed game. Can I always win this game? Is there a winning strategy? So for this one here, you have 7 tries. So no matter what number the computer picks, can I guarantee that I will always win? Go ahead, Ella.
Yeah, I think there is a way of like maximizing.
That's
like
not
our-
my question. My question is this particular game that we just coded, can I always win it?
I think so.
Okay, that's one.
I
Somebody else?
I disagree.
It has a little bit to do with the collatz
No,
thing
no,
because
no,
It's not
really.
winnable. It's not
Uh,
guaranteed.
Okay, so I'm gonna give you an example here. If you have 1,000 tries, certainly there is a winning strategy. You ask, is it 1, is it 2, is it 3, is it 4? You're not gonna run out of tries, so there is a winning strategy. What number of tries do you think guarantees? So 1,000 guarantees me a winning strategy. What number? I can tell you that 7 doesn't. We can prove this. The 7, you cannot guarantee it with the 7. What number of tries do you think guarantees me that I can always win this game?
10.
How many?
10.
10. It is 10. And I know that many of you are not happy when I give you these questions that have to do with logs, but this has to do with logs. Okay, we're gonna learn this. So actually, this is the one that I wanted to do, 10 tries. I want us to play this game and we better win because there is a way to play this such that you always win. Okay, so what I wanna, if we lose, you are not a very good guesser, and go read up on binary search. We're gonna learn about binary search and what does this have to do with binary search? Okay, so let's play the game. We better win. Last class we lost, so let's do better than the last one. And let's tell the users, just so we know the count, how many guesses we have. Here, whenever we have a wrong guess, we can tell a user guesses. We can tell the player how many guesses they're left with. All right, and here we want the same, right? Type how many tries are we left. Okay, so
Are we
let's
supposed
play.
to say? Are you
This
supposed to
is
say
25.
tries equals to tries minus 1 in the while loop as well?
Oh,
Or?
yes, of course. Thank you, Jay. I think that was
And your
Jason.
tries are ties.
Yeah. All right,
That
exactly.
too, and tries are try. You
I
put
mis-
ties instead of tries.
Okay.
In the F and Elif.
All right, so let me do all of these. Hopefully I pick them all up. If else. So hopefully now this works. All right, so let's play a game. What should be my first guess?
10.
10?
No,
500.
500.
500.
Okay, it seems that majority says 500. Okay, it's wrong. 9 guesses left. It's too high. What should be my next guess?
250.
250.
250. What should be? It's too high. So we are between
125.
1 and
25.
125.
What's the next one?
125.
125. It's too
75.
high. So we are between 1 and 125. What's the next one?
62.
63.
Yeah, one of the two, 62 or 63.
Okay, 62 or 63. It's too low. So we are between 63. We are between 63 and 125. Where's the next one?
94.
80.
94.
75.
94.
And
94.
94.
Okay, I'm having
94.
majority seems to say 94. It's too high. So we are between 63 and 94. What's the next one? We have only,
78.
80.
87.
80.
what is the next one?
78.
78.
78 or 77.
8.
78. Okay, 78.
78.
Majority. Oh my God. No.
Oh,
That was not the
Go.
point. We were lucky.
Okay.
This was
Good
easy.
Wow.
Well, this is we were lucky. This was not. You should play again by yourself. In the previous class, it really happened. What I hope it will happen, which is that if you make a tiny mistake, you can lose, because on guess 2, we end up with 2 numbers. So not guess 2, last guess, we had one more try, but if you end up with 2 numbers, it's over because you can lose, right? And we did pick the wrong one. We had 50% chance to pick a wrong one, and we did. If you play correctly with 10 guesses, the only thing that can happen if you make it to guess 10 is that you end up with only one possibility, and that therefore you win. What this have to do with logs and with your homeworks, it has to do with if you go and guess in the middle of the range, that eliminates half of the possibilities. So if you start with an N, with 1 question, you halve the number of possibilities. You repeat the strategy, you will now have a range of 500 numbers. You go to the middle with the second question, you eliminate half of that. So, and you want to end up down to 1. So it's exactly that question you had in assignment number 1. You're starting how many questions do I need to end up with 1 possibility, which is N. So I'm going from, with 1 question, I go from N over 2. With the second question, I'm going from N over 2 to N over 4. With the third question, N over 4, from N over 4 to N over 8, and so on. So basically, as long as you give me log base 2 of N tries, I can always win if I know what I'm doing. So that means, if forget about 1,000, so tell me as the last thing in this question, if the computer picks a number between 1 and 1,000,000, how many tries is enough to win?
20.
20, exactly, because log base 2, you can check in on the, so it's basically log base 2 plus 1, but so basically it's 20. It's a seal of that, okay? All right, so that's it for today.